In the first video, we set up the drive and we did some system testing. In the second video, we learned how important it is to get a clean feedback signal, and then we set up PID using the trial and error method. In this video, we're going to set up PID using some formulas that don't require all the trial and error guesswork. Now, before we do that, we need to linearize the system feedback. It's really important to understand that PID works best when the manipulated variable tracks one-for-one with the process variable. That is, when the frequency output's at 50%, the feedback signal's at 50%. When the frequency's at 60%, the feedback's at 60%, etc. It'll be rare that you get a system that cooperative, and as we saw in the first video, ours is no different. Let's take a couple quick measurements and see where we stand. Normally, you would turn PID off and simply vary the drive frequency and watch the result on the feedback signal. But that would require entering the frequency in hertz and then converting it to percent. And since we already have PID set up with PI and D all set to 0, this stuff isn't doing anything, so we can just modify the output frequency by adjusting the offset, which is already in percent, so we don't have to do any conversions. We know from the first two videos that the drive needs to operate in this frequency range to maintain a system pressure of 6 psi. That's this percentage range. So how about we run our measurements from 45 to 70% of the drive's 60 Hz range. Let's monitor the feedback signal using the GS4 scope function and set the drive frequency to 45%, 50%, 55%, 60%, 65%, and 70%. You might want to use finer steps, but for our demo, every 5% is fine. Now we can read the process variable level for each step. If I bring up a spreadsheet, enter my frequency percentage range in the first column, and make the second column equal the first column, we'll call that line, and do a scatter plot, we get the straight line we would like for our system to be. Let me modify the chart axis a little bit to show just the range we're interested in. That's better. Now if we entered the measured feedback in percent, copy that column, and paste it into our plot, we see our system is nowhere near linear. So let's modify the measured data by a slope and an offset. So our modified data will be this guy times the slope plus the offset. And we need to make sure those are fixed values by putting $signs in here. And let's repeat that for all rows. Copy that column and add it to the plot. If we bump the offset up just a little bit, we see our new data moves away from the measured data. I'm just going to mess with the slope and the offset until I get a line that's as close to the straight line as I can. Yeah, that looks pretty good. So by multiplying the feedback signal by this slope and adding in this offset, we get a new feedback signal that's close to linear over the frequency range we care about. That'll make PID really happy. Now we just take those and put them in parameter 412, which is the slope or gain for analog input 1, and parameter 4.10, which is the offset for analog input 1. Parameter 411 enables that offset. Don't forget that one. The offset won't work without it. Okay, the feedback signal in percent should now be tracking the output frequency in percent. Let's see if it is. If we go back to the main screen, we see that the feedback signal is now roughly 51.8%, which is exactly what our current offset is. Perfect. If we bump that offset up to 56% and then to 61%, then we see on the scope that the feedback signal also went to roughly 56 and 61%. Exactly what we want to see, a reasonably linear system where the feedback signal tracks one-for-one with the frequency output signal. If this blue frequency trace wasn't in hertz and it was in percent, then guess what? We would see that laying right on top of this yellow feedback signal trace, wouldn't we? Now, because we changed the feedback signal, we need to change the set point, right? Before, we knew we needed 40% here because 40% of the sensor's 15 psi range is 6 psi. So we put 24 hertz here, which is 40% of the drive's frequency range. Well, that doesn't work anymore because we modified the feedback signal. So what should this be? Well, we know we need 51.8% here to get 6 psi with one valve open, right? And we just linearized the sensor feedback to basically match the drive frequency in percent, so we need 51.8% here too, which is this in hertz. Well, that's easy. Whatever we put here, we also put here. Now that we have a linear system, we can do the formula method for PID. To do that, we just measure a couple things, plug them into a formula, and we're done. And the best part is, we do all of this open loop. That is, PID is not enabled during these measurements, so you're not risking sending your system into oscillation. Normally, you start this process by measuring the process gain, which is how much does the process variable change when we change the manipulated variable. But since we just linearized our system, so a change in the manipulated variable gives us the same answer in the process variable, our process gain is 1, so we can skip that step. The next step is to verify your hysteresis. That is, does the process return to its original value when you step away and back again? Well, we know ours does, so our hysteresis is 0, and we can skip that step. For these two guys, you step the frequency output and make measurements on the feedback signal. Well, we just did that a minute ago when we verified the modified feedback signal linearity. So let's bring that plot back up and use it for our measurements. We only need to measure two things. When do we reach 25% and 75% of the desired output? We see the difference between one step and the next is this, so 25% of that is this, and 75% is this. We just move the cursor to the 25% level and note the time, and move the cursor to the 75% mark and note that time. Given those measured values, we calculate the time constant using this formula and the dead time using this formula. And given those, we calculate the three numbers we need using these formulas. The process gain is 1, but what are these A and B numbers? Well, for those, you go to this chart and pick the ones you want. First, you choose which algorithm you'll be using, P only, P and I, or P, I, and D. We'll use the P and I row, so we have an apples-to-apples comparison with the previous video that didn't use D. Do we have a system that has a changing load or a changing set point? Well, we're changing the load. We're opening and closing the valves. So that means we want these A and B constants. Plug everything in, and we have our answer. I use this spreadsheet that does everything for me. I just enter the two measurements here, and I get the PID numbers here. Easy. Wait a minute. This p-value is double what we got in the last video. In that video, the system went berserk at a p-value of 4 and was starting to oscillate at 3.5, so we backed off to a p-value of 3. How can this possibly be right? Well, I triple-checked my measurements and number crunching, so let's just give it a shot. Go to parameter 713 and enter P, then go to parameter 714 and enter I. I'm going to rezoom everything so we can see the whole picture. Start recording, and then open and close the valves. Holy cow, that's gorgeous. The drive is now automatically adjusting the blue output frequency to maintain the yellow system PSI at our green set point. And all we did was linearize the system and take two open loop measurements. That's incredible. So why did this large P work here, but it didn't work in the previous video? Well, because we linearized the feedback signal. Remember, we said PID really likes to have a linear system, right? Well, now you see the dramatic result. Would we have gotten similar results in the previous trial and error video if we had linearized the system first? Well, sure. Looks like the I parameter needs to be more aggressive. Let's take it all the way down to the same number we had in the previous video. Run that, open the valves, and close the valves. And yeah, that looks a lot better. Why did we have to adjust I? Well, because we had filtering turned on when we did our measurements. You're supposed to turn that off before doing the time measurements, but our signal was so bad that I skipped that step, and I knew I could just adjust it when we were done. So you must be wondering, where did these magic formulas come from? This presentation was an adaptation of something called the PID blueprint. Now beware, that is not an AutomationDirect product, so please don't call tech support and ask any questions about it. They won't be able to help you. Instead, go to this website to learn all about it or contact the author. I do need to warn you, don't try what I did here on any random PID tuning process. What you saw here was tailored for this project. The PID blueprint is a much broader scope and covers a much wider range of PID loop styles. I do plan to do some more videos showing the other PID variations in the future, so be sure to click here to subscribe to our YouTube channel so you'll be notified when those are published. Click here to learn more about the GS4 family of variable frequency drives, and click here to learn about Automation Direct's free award-winning support options.